Okay, so today we're gonna do a deep dive into reticular chemistry. And for this deep dive, we actually have two different research papers and a news article.
Sounds good.
Now, reticular chemistry, this is chemistry, but it's big. You
Yeah.
know, we're talking about building things at the molecular level.
Yeah, it's sometimes called reticular synthesis, and it's really a field that's grown a lot in the last 30 years or so.
So the basic idea is you've got these like molecular building blocks, and you use them to create these large structures.
Right, and the key here is we're talking about extended structures that are held together by really strong bonds.
Oh, so it's not just like, molecules sort of weakly attracted to each other. This is like really building something.
Exactly. It's about creating these robust frameworks that have specific properties and functions.
And I think one of the most fascinating things about reticular chemistry is this concept of addressability. I mean, it sounds like something out of a sci-fi movie.
Well, kind of is like science fiction come to life.
Hmm.
With addressability, you can actually target specific locations within these frameworks and modify them.
So you're saying we can like tweak these structures at the molecular level? That's insane.
It is pretty incredible. It's like having a blueprint of a building where you can not only change the purpose of each room, but also add entirely new features exactly where you want them.
Okay, so we can build these incredibly complex structures and then we can fine-tune them for specific purposes. Where do we even begin to explore the applications of something like this?
Well, one of the most promising areas is gas storage and separation.
Oh, right. Like with those metal organic frameworks, MOFs, I've heard about those.
Exactly. MOFs are a great example of reticular chemistry in action. They have these incredibly porous structures with huge surface areas.
So it's like a molecular sponge capable of soaking up and storing gases.
Precisely.
Hmm.
And because we can design the pores of these MOFs with such precision, we can target specific gases like hydrogen or carbon dioxide.
Okay, I'm starting to see the potential here. We could use MOFs to store hydrogen for clean energy or to capture CO2 from industrial emissions.
Exactly. And that's just the tip of the iceberg. MOFs are also being explored for things like water harvesting, drug delivery, even catalysis.
Wait, hold on, water harvesting. You're telling me we can use MOS to pull water out of thin air?
Well, not exactly thin air,
Hmm.
but certain MOFs can capture water molecules from the atmosphere even in arid environments.
That sounds like something out of a science fiction novel.
It does, doesn't it? But it's a real technology with the potential to address water scarcity in some of the driest regions of the world.
This is incredible. So we've got these porous materials that can store gases, filter water, deliver drugs.
Yeah.
I mean, the possibilities seem endless.
They really do.
Yeah.
And what's even more exciting is that we're just scratching the surface. We're constantly discovering new building blocks and new ways to assemble them.
It's like having a molecular Lego set with an ever-expanding collection of bricks.
And the more we learn, the more we realize how much potential there is in this field.
But I imagine it's not all smooth sailing. There must be some challenges in building these complex structures at such a small scale.
Oh, absolutely. One of the biggest challenges early researchers faced was something called the crystallization problem.
The crystallization problem, what's that?
Basically, it was incredibly difficult to get those molecular building blocks to assemble into a perfectly ordered crystalline structure.
So it's not just about connecting the pieces, it's about connecting them in the right way to form a stable and functional material.
Precisely. And it took a lot of ingenuity and trial and error to overcome this challenge.
So who are some of the pioneers who figured this out?
Well, two names that come to mind immediately are Omar Yaghi and Michael O'Keefe.
I've heard of Yagi. He's like a rock star in the world of reticular chemistry.
He is. He's done groundbreaking work in synthesizing those first MOFs and COFs.
And what about O'Keefe? What was his contribution?
O'Keefe is known for his work on the geometry and topology of these frameworks. He helped us understand the fundamental principles behind their structure and properties.
So it was a combination of Yagi's experimental skills and O'Keefe's theoretical insights that really propelled the field forward.
Absolutely. It was a beautiful example of scientific collaboration leading to major breakthroughs.
And those breakthroughs have paved the way for this incredible field we're exploring today.
A field that's changing the way we think about materials and their potential applications.
Now, I know we've been focusing on MOFs, but there's another type of framework that's gaining a lot of attention these days, and that's COFs.
Ah, yes, covalent organic frameworks.
So what makes COFs different from MOFs?
Well, the key difference lies in the building blocks. MOFs, as we discussed, use metal ions or clusters as their nodes, while COFs are built entirely from organic molecules.
So it's like comparing a steel frame to a carbon fiber frame. different materials, different properties.
Exactly. COFs tend to be lighter and more flexible than MOFs, and they often have unique electronic properties.
So what kinds of applications are COFs being explored for?
Well, they're showing a lot of promise in areas like gas separation catalysis and even optoelectronics.
Optoelectronics. So we could potentially use COFs to create new types of solar cells or LEDs.
Exactly. The possibilities are really quite remarkable.
Hmm.
And as we continue to explore the diversity of organic building blocks, we can create COFs with an even wider range of properties and functions.
This is all so fascinating. It's like we're entering a whole new era of material science where we can design and build materials with atomic precision.
It is an exciting time to be working in this field. And as we delve deeper into the world of reticular chemistry, I think we're going to see even more groundbreaking discoveries and applications.
And I'm sure we'll have plenty more to discuss in our next deep dive into this incredible field.
I look forward to it.
You know, with all this talk about molecular Legos and building blocks, I can't help but wonder what these structures actually look like. I mean, are there pictures, videos? Can we actually see these intricate frameworks?
Oh, you're in luck. One of the most captivating aspects of reticular chemistry is that these structures are often visually stunning.
So we're not just talking about functional materials, we're talking about molecular art.
You could say that if you search online for images or videos of MOFs and TOFs, you'll be amazed by their intricate beauty and complexity.
That's fantastic. I'm definitely adding that to my to-do list after this. Okay, so we've covered a lot of ground here about the nuts and bolts of reticular chemistry. But what does this all mean for the average person?
That's a great question, and it's important to remember that reticular chemistry isn't just some abstract scientific concept. It has the potential to impact our lives in very real and tangible ways.
So it's not just about pushing the boundaries of science, it's about using those advancements to make a difference in the world.
Precisely. And the potential applications we've discussed today are just the tip of the iceberg. As we continue to explore this field, I think we're going to see even more incredible breakthroughs that will benefit society as a whole.
Like what? Can you give us a glimpse into the future?
Well, one area that I'm particularly excited about is the development of new materials for energy storage.
Oh, yeah. Energy storage is huge these days. Everyone's talking about batteries and renewable energy.
Exactly. And reticular chemistry could play a major role in developing the next generation of batteries and supercapacitors.
Imagine a world where we could store energy from solar panels and wind turbines more efficiently and reliably.
That's the dream. And with reticular chemistry, we're getting closer to making that dream a reality.
That's amazing. And what about other areas? What other challenges could reticular chemistry help us address?
Well, another area that's ripe for innovation is environmental remediation.
You mean like cleaning up pollution?
Exactly. Imagine MOFs and COFs that can selectively capture and remove pollutants from water or air.
So we could use these materials to clean up industrial waste or even to filter out harmful toxins from our drinking water.
Precisely.
Wow.
And that's just one example. The potential applications in environmental remediation are vast, and I think we're going to see some major advances in this area in the coming years.
It's incredible to think that we can design materials at the molecular level to tackle such large-scale problems.
It is, and it speaks to the power of chemistry and material science to address some of the most pressing challenges facing our world.
So we've got clean energy, environmental remediation. What else is on the horizon for reticular chemistry?
Well, one area that's gaining a lot of attention is the development of new materials for healthcare.
Oh, right. Like those drug delivery systems we talked about earlier.
Exactly. But it goes beyond that. We're talking about materials that can be used for sensing diagnostics, even tissue engineering.
So reticular chemistry could help us develop new tools for diagnosing and treating diseases.
Absolutely. And with the ability to design materials with such precision, I think we're going to see some truly transformative advances in healthcare in the coming years.
This is all so inspiring. It's like reticular chemistry is opening up a whole new world of possibilities.
It is, and it's a world that's full of potential to make a positive impact on society.
But with all this talk about the potential benefits, it's important to acknowledge that there are also potential risks and challenges.
You're absolutely right. Like any powerful technology, reticular chemistry needs to be developed and used responsibly.
So what are some of the ethical considerations we need to keep in mind?
Well, one concern is the potential for unintended consequences. We need to make sure that these materials are safe for both human health and the environment.
So we need to carefully evaluate the toxicity and environmental impact of these materials before we start using them on a large scale.
Absolutely. And we also need to consider the potential for misuse. Imagine an MOF that could be used to selectively filter out certain gases from the air.
That sounds pretty benign. What's the risk there?
Well, in the wrong hands, such a material could potentially be used for malicious purposes, like creating chemical weapons.
Oh, I see. So we need to be mindful of the potential for dual-use technologies and develop appropriate safeguards to prevent misuse.
Exactly. And it's also important to consider the issue of access and equity. We need to make sure that the benefits of reticular chemistry are shared widely and that these technologies don't exacerbate existing inequalities.
That's a crucial point. We don't want to create a world where only the wealthy and privileged have access to these life-changing advancements.
Exactly. We need to ensure that reticular chemistry is used to benefit all of humanity, not just a select few.
So as we move forward with this exciting field, it's important to proceed with both caution and optimism.
I couldn't agree more. It's about finding the right balance between pushing the boundaries of science and ensuring that those advancements are used for good.
And that requires a thoughtful and inclusive approach that involves scientists, policymakers, and the public alike.
Absolutely. It's a conversation that we all need to be a part of.
And it's a conversation that I'm sure we'll continue to have as reticular chemistry continues to evolve and shape our world.
I look forward to it.
Okay, so we've talked a lot about the what and the how of reticular chemistry, but I think it's also important to step back and consider the why.
The why?
Yeah, why should people care about this? What's the big picture here?
Ah, I see what you mean. Well, I think the big picture is that reticular chemistry has the potential to solve some of the world's most pressing problems.
Like what? Give me some examples.
Well, we've already touched on a few: clean energy, water scarcity, drug delivery. But it goes beyond that. Reticular chemistry could also help us develop new materials for electronics, agriculture, even space exploration.
Wow, space exploration, that's pretty far out.
It is, but think about it. We need materials that are lightweight, strong, and can withstand extreme temperatures and radiation. That's where reticular chemistry comes in.
So we could potentially use these materials to build spacecraft or habitats on other planets.
Exactly. The possibilities are truly limitless. And that's what makes this field so exciting.
So it's not just about building cool structures, it's about building a better future.
Precisely. It's about using our knowledge of chemistry and material science to create a more sustainable and equitable world.
Well said. I think that's a great message to leave our listeners with. But before we wrap up, I want to make sure we highlight some of the key takeaways from this deep dive.
Sounds good.
So first, reticular chemistry is all about building with molecules, creating these intricate frameworks with specific properties and functions.
Right. And we've seen how these frameworks can be used for a wide range of applications, from gas storage to drug delivery.
And we've also learned that this field is constantly evolving, with new discoveries and applications emerging all the time.
Absolutely. It's a truly dynamic and exciting field to be a part of.
And as with any powerful technology, it's important to consider the ethical implications and ensure that these advancements are used responsibly.
Couldn't agree more. We need to have a thoughtful and inclusive conversation about the societal impact of reticular chemistry.
And that conversation needs to involve everyone from scientists and policymakers to the general public.
Exactly. It's a shared responsibility to ensure that these technologies are used for the benefit of all humankind.
Well, I think we've covered a lot of ground today. This has been an incredible journey into the world of reticular chemistry.
It has, and I hope our listeners have enjoyed the ride.
I'm sure they have. And if you're interested in learning more about this fascinating field, we'll be sure to include some links in the show notes.
Great idea. And who knows? Maybe this deep dive will inspire some future reticular chemists out there.
That would be amazing. Well, that's all the time we have for today. Thanks for joining us on this deep dive into the world of reticular chemistry.
It's been a pleasure.
And until next time, keep those minds curious and those imaginations sparked.